Okay, great. So here is the Jamboard. I think I have posted in the chat both a link to the Jamboard. You can also watch, I'll share my screen so you can watch it in real time, but you can also, if you click on the link, then you'll be able to scroll backwards and forwards through the slides, which has advantages. I posted a link to the Jamboard in the chat, as well as links to the 2 exercise packages. So a reminder, there's one fully optional exercise package that gives some background on just the general theory of cohomology of groups, including ideas surrounding things like Bieri-Ekman duality. And there's also a link to at least the current draft, which is close but not quite polished yet, of all of my and Peter's lectures, which is in certainly more detail than the actual lectures will be, possibly more detail than you want. There's also the current version of the exercises in there. So take a look at that link if you're interested. Great, thank you. So let me resume my lecture, and let me start by recapping what happened in the previous lecture, just so we're all back on the same page. So the broader goal of these lectures, of my and also Peter's current research programs, is largely to the following. It's to understand the high degree cohomology of these groups SL and R, and we'll continue. R is a number ring in a number field F. R and F will be, I'll use that notation throughout this lecture. Okay, and the goal of my 3 lectures is to prove this result originally due to Lee and Sharba that says if R is Euclidean, if my number ring is Euclidean, then if I look at cohomology in the VCD with rational coefficients, so this is the top degree we could possibly have non-vanishing rational cohomology groups, well then in fact that group does vanish. That's the goal of my lectures. Okay, and as per this Borel-Serre duality result, to prove this result, it's equivalent to show down here that the SL and R coinvariants of the Steinberg module vanish when R is Euclidean. Okay, this is our goal. And so what have we done so far? So far, we showed that if we assume this result of Ash and Rudolph, so Ash and Rudolph proved this result, that when R is Euclidean, the Steinberg module is generated by these integral apartment classes. So it's generated by these apartment classes where the corresponding frame comes from a basis for R to the n. When R is Euclidean, we have generation by these integral apartment classes. And then we showed that under those assumptions, we can just find an element of SLN R that negates each of these generators, and we're done. So far, let me, oh, I'm sorry, I was moving on my tablet, but not on my screen. Let me, sorry, here's the Ash-Rudolph theorem. So we showed, this is the Ash-Rudolph statement saying that we have generation by integral apartment classes. And then we showed that we can find elements of SL and R that negate each of these integral apartment classes. And so we're done in the case that R is Euclidean under the assumption of the Ash-Rudolph theorem. Okay. So here's lecture 2. And okay, so again, the goal is to show that we have vanishing when R is Euclidean. This is Lee Sharba. And so far we've proven in lecture 1 we showed that this is the case, assuming this result of Asteroidal. And today, or this lecture, lecture 2, we're going to give a proof of Asteroidal, although we'll give that proof assuming something else that we'll then have to prove tomorrow. So we're converging towards this result. Okay. And again, so we did not use the original Lee-Sharba proof. We were using this result of Ash-Rudolph, which actually predated Lee and Sharba. And again, we're going to give a proof of Ash and Rudolph, which is not the original proof. We're going to use a different method. So we're going to use a proof based on work of Church, Farb, Putman. And a reason for taking this particular approach to these results is that we're going to use methods that generalize to proving results for vanishing of the codimension I cohomology of SLN Z for higher codimension. Okay, and maybe I should stress I would be perfectly happy if you want to assume throughout this lecture and my next lecture, if you want to just assume that R is the integers, then that is great. These results are contentful in that case. And that's, in my mind, the most important example. Okay, so we want to prove this Ash-Rudolph result, which states that the Steinberg module is generated by integral apartment classes when R is Euclidean. And we're going to do this using some simplicial methods. So let me review a little bit of terminology from the theory of simplicial complexes. Okay. So, right off the bat, let me remind us that the definition of a simplicial complex is actually quite constrained. So, for example, here are two pictures of, I don't know, what you might call a delta complex. These are both delta complexes that are not simplicial complexes. Okay. We'd have to subdivide these both more in order to get simplicial complexes. And part of the problem is a simplicial complex is something I build by gluing simplicials together, but it's subject to the constraints. First of all, every time I glue in a simplex, I have to glue every single one of its vertices to distinct vertices in the zero skeleton. Okay, so this is not a simplicial complex because I've glued both vertices of this edge to the same simplex. That's not allowed. And here, this guy is not a simplicial complex either, because another rule with simplicial complexes is that I need to, that if I have any subset of my vertices, that subset of vertices is going to span, it either spans a simplex or it doesn't. It cannot span more than one simplex. Okay, so neither of these are valid simplicial complexes. The smallest simplicial complex structure I can put on a circle is this one. Okay, and in fact, so I guess this is a trade-off. On one hand, to put a simplicial complex structure on a given topological space, I might have to subdivide my simplicial, if I start with a delta complex structure, I may need to subdivide it a lot before I get to a valid simplicial complex structure. But the flip side is that simplicial complexes are very well behaved combinatorially. In fact, the data of a simplicial complex is a vertex set, and then a collection of subsets of the vertices I just need to specify which subset spans simplices. Okay, so the flip side is that simplicial complexes have this really nice combinatorial characterization. And we can completely refer to them just by talking about subsets of the vertex set that span simplices. Also, which will be relevant in the next lecture, it also means that in order to define a continuous map between simplicial complexes, it's enough to define it on the vertex set and then just make sure that every time a collection of vertices spans a simplex in the domain, that their image spans a simplex in the codomain. So again, understanding continuity of maps between simplicial complexes is very combinatorial. Great. Okay, so here's another definition that I will use frequently in the next few lectures, that if I have X, if X is a simplicial complex, if X is a simplicial complex and sigma in X is a simplex, okay, let's say, so again, I can specify a simplex just by writing down its vertex set. And in fact, if I remember an order on the vertex set, then I remember an orientation on my simplex, which is sometimes useful, especially if we're dealing with homology and want to make sense of signs. Okay, so here's my vertex, simplex written as a vertex, which I'll be a little agnostic about whether or not I want to remember the ordering on those vertices. Here's the definition. The link of sigma is a subcomplex of X defined as follows. This is the subcomplex of X of simplices of the form T0 up to TQ such that S0 up to SP and then T0 up to TQ is a simplex. So in other words, what I do, let me draw a picture. We'll go ahead a page. Oh, shoot. Sorry, let me done this. Let me duplicate this and then clear it. Okay, yeah, that's good. Okay. And then I'll just duplicate it again so I have more of these slides that I like. Sorry about this. Technical problems. Okay, great. All right, so we're on page 7. All right, so here's a picture of a link. So maybe here's my simplicial complex. Let's say this is a triangle, and maybe that's just a loop over there. And here's my simplex sigma. It's just a vertex in this case. So the link of sigma, what I do is I look at all of the simplices that contain sigma as a face. In this case, there are 3 of them. Oops, in this case, there are this triangle and these 2 edges. And then I take the opposite faces of those simplices. So I take this point and this edge, and this is the link of sigma. Okay, so that's the definition of a link, which we'll use a lot. All right. And another reminder that we'll need for the following definitions is about connectivity. This is true. This is not just simplicial complexes, any topological space. If X is a topological space, then, well, first of all, every topological space is what we call -2 connected. That's a vacuous condition. Then X is the statement that it is -1 connected. That's equivalent to being non-empty. The statement that it's 0 connected, that's equivalent to being path connected. Being 1 connected is the same as being simply connected. As in path connected and vanishing fundamental group. And then in general, the space is deconnected if and only if the first D homotopy groups vanish. Okay, great. So this is a very important definition in the, I guess, stability literature from algebraic topology more generally. And we are going to use it to state the following condition, another definition, which is going to be somehow the crux of the main results from today's lecture and the next lecture. Okay, so here's our key definition. Again, I'm going to talk about simplicial complexes. So X in this case is a D-dimensional simplicial complex. Oops. Okay. And the definition X is what's called Cohen-Macaulay. Which I'll abbreviate CM. If the following two conditions hold. So the first condition is that X is D-1 connected. Okay, so it's homotopy groups from degree 0 up to degree D-1 vanish. And the next condition is that its links are also highly connected. So if I take the link of a simplex sigma, then it has to be D-2 minus the dimension of sigma connected for all simplices sigma in X. Okay. So the slogan, I think what you should have in mind when you hear this condition, you should have in mind the slogan that this says that X is X and its links are as highly connected as the standard simplicial structure on a D-sphere or a wedge of D-spheres. Well, certain wedge of D-spheres. Great. So some examples, which I'll leave as exercises. So first is to check that the standard n simplex and its boundary are Cohen-Macaulay. Okay. In contrast, here's an example. Let me draw. Simplicial structure, two triangles wedged together. This picture is not Cohen-Macaulay, even though it's contractible. So it's as highly connected as you could hope. It's infinitely connected. However, if we look at the link of this vertex here, it consists of two edges the link of that vertex is not connected. It's not even 0 connected. It's -1 connected. And that's not high enough to satisfy the definition of Cohen-Macaulay for something that's two-dimensional. So even though this thing is contractible, somehow its links aren't good enough. Okay, and so that's an example of a complex that's not Cohen-Macaulay. Great. Okay. And so we're going to use this concept to study, in fact, several different simplicial complexes that are related to the Tietz building. And we're going to use that today to prove the Asteroidal Theorem. Okay, so the main new complex that I want to introduce for today's talk is the complex of partial bases. And for the purposes of this definition, really it makes sense if R is any ring. I think, well, let's at least assume R is a PID, but R in principle could be any ring. And F, again, is going to be the field of fractions of R. Okay. Okay. So here's our definition. A collection of vectors in Rn is called a partial basis. Called a partial basis if it is a subset of a basis, possibly equal to a basis. Could be a full subset. Okay. And so a couple of straightforward exercises. One that if we take a single vector in Rn, then this is a partial basis if and only if V naught is primitive, i.e. its entries, the ideal generated by its entries is the ring R, so its entries are coprime. Okay, any vector with that property you can extend to a basis. Another example is that if we look at, let's say, here's a collection of vectors this is not a partial basis for Z3. So that's also left as an exercise, but there's something goes wrong with determinants in this condition, in this example rather. So this is an example of a pair of vectors that fail to be a partial basis for Z3. Okay. And so now our definition is the following complex that I'll write PB n of R. This is the complex of partial bases. Where it's defined as a simplicial complex, abstract simplicial complex. The vertices are primitive vectors. And a collection of vertices spans a simplex if and only if they form a partial basis. Okay, so this is the right, this is the complex of partial bases. Let me go on to the next page. I'm on page 8. Oh, and I should duplicate this page so I have a page for next time. Okay. Right. Oh, and let me make the comment that for technical reasons, we are going to consider both this complex and its barycentric subdivision. So a reminder that in general, the barycentric subdivision of a simplicial complex is what you get by placing a new vertex in the center of every single existing simplex. So in general, the vertices of this new complex correspond to the simplices of your original complex, and a simplex in the barycentric subdivision corresponds to a flag, to a chain of simplices under inclusion in the original complex. And importantly, this barycentric subdivision operation, it changes the simplicial structure. It does not change the homeomorphism type of the complex. So let me just write down in this specific case, note that this complex of partial bases is homeomorphic to its barycentric subdivision, which we will sometimes work with. And this is the complex where the vertices correspond to partial bases. And the simplices correspond to a chain of partial bases under inclusion. Okay, so sometimes we'll need this variation, but they're homeomorphic as topological spaces. Okay. And so what we are going to do in the last half hour, last 35 minutes of of the second lecture is the following. We are going to prove that the Steinberg module of a Euclidean ring is generated by integral apartment classes under the assumption of the following result due to Mason. And the result of Mason from the 70s, I hope I'm pronouncing the name correctly, I may not be, is that if R is Euclidean.
I mean, he's Dutch. I don't think he's Mason, but I don't know how to pronounce it correctly either.
I would be grateful if anybody in the audience knows how to pronounce this name correctly. Please speak to me afterwards. And my advance apologies to everyone.
You should ask Sanders. He would know.
I should ask Sanders. That's a good idea. Okay, great. So the result is that the barycentric subdivision of this complex of partial bases is Cohen-Macaulay. So, right, so exercise, this complex has dimension n-1. And so again, the slogan is, for Cohen-Macaulayness, this is the statement that this complex and its links are as highly connected as a sphere of dimension, of a sphere with the standard simplicial structure of dimension n-1. All right. And so our goal for this lecture is to show that under the assumption of this result of Mason, we can prove the Asteroidal Theorem, which states that the Steinberg module of our Euclidean ring is generated by integral apartment classes. Okay, and then in tomorrow's lecture, we'll prove this result. Okay. So the key to this step, the key to proving this step is the following lemma that's due to Quillen. So here's a lemma due to Quillen. And here's some notation. If X is now a poset, then I'm going to write X for its geometric realization. So this is the simplicial complex where the vertices are the elements of X. And the simplices correspond to chains in X. Okay. And I'll need another piece of terminology, which is that the height of an element little x in X is the maximum value of P such that there exists a chain of the form x0 less than x1 less than xp, which is equal to x in the poset. Okay, that's the height of an element. And notice this chain, its height P if this chain has length P plus 1. So this chain in the realization gives me a p-dimensional simplex. Okay, and with that notation, here is our key lemma, which is due to Quillen. And which I won't prove this lemma at all, but the basis is a spectral sequence construction, which I think Peter will talk about in more detail, or at least allude to in more detail. I
don't think I will actually have time for it, but
maybe we won't. Okay, there's an appendix. Thanks to Peter, there's an appendix in the package of notes about how the spectral sequence works for anybody interested. But for now, we'll just black box this result of Quillen. And it says the following, that if I have a map of posets, so that means it's a map on the underlying set that respects the poset relation. And in fact, I want to assume something even stronger. I want to say it's a strictly increasing map of posets. So it respects even strict inequalities. Okay. Under the assumption that Y is Cohen-Macaulay of dimension D, and the downward fibers of this map, so let me define that, for every Y in the domain, the downward fiber of this map is defined as follows. It's a subcomplex or a subposet of X of all elements that map to something smaller than Y. So it's not just the pre-image, but it's the pre-image and everything beneath it in X. These downward fibers have geometric realization that are Cohen-Macaulay of dimension equal to the height of Y. Under these two assumptions, then the geometric realization of X is Cohen-Macaulay. And what we'll use is that if we look at the induced map on the reduced degree D homology groups, then this map is surjective. Okay. So our goal is to use this Quillen poset lemma, map of posets lemma, in order to leverage the high connectivity result, the Cohen-Macaulay result for the complex of partial bases, in order to prove that the that the Steinberg module of the Euclidean ring is generated by integral apartment classes. We have some time left to do that. Excellent. Okay, so here we go. Here's the proof of Ash-Rudolph. So this is the proof of generation of Steinberg. By integral apartment classes for R Euclidean.
Couldn't D have dimension less than the dimension of, couldn't X have dimension less than the dimension of Y?
Could X have dimension less than the dimension of Y?
Less than D, in which give a surjection.
Let me see. So I think we'd have to think about part of the conditions. So let's see here. So it's strictly increasing. So that probably says that it can't be. Sorry, less than the dimension of Y. Oh yeah, sorry. So this condition, I think you could, I think this condition on the fibers implies that the map has to be surjective.
Okay, so sorry. Okay, sorry.
Yeah. Yeah. So right. So great question. That was kind of brushed under the rug. But yes, I think it follows from this condition. In fact, tells me what the dimension of these downward fibers has to be, and it means in particular that if I take any Y, this preimage has to be non-empty. So yeah. So I think.
Yeah, the smallest height has to be 0. The smallest height of an element is 0, and so it has to be at least of CM dimension 0, and that means it's non-empty. Yeah.
Yeah. Thank you. Sorry, that was a subtle point, but yes, the map has to surject, which is somehow buried in these conditions. Okay, great. Okay, so we are going to prove the Ash-Rudolph theorem on generation by integral apartment classes using the following map of posets. So first of all, I'm going to let Y be the poset of proper non-zero. Excuse me, summands of Fn under inclusion. And I'm going to let X be the poset of proper partial bases of Rn under inclusion. Okay. And the map, my map of posets, it's an exercise to check it strictly increasing, not a very hard exercise. The map of posets takes a partial basis for Rn to its span over the field of fractions. Okay, so this is our map of posets. And I'm going to leave it partly as an exercise to verify all of the hypotheses of Quillen's lemma. And there are, some of these exercises are much more structured in the notes document that I've attached, but let's just go down the list. See what we need to check. Okay. So first of all, not too hard to check that F is strictly increasing. One basis is a strict subset of another, then you get strict containment of the corresponding spans. The next thing we had to check was that oh, actually, sorry, let me back up and just make the observations. I should have said this at the top, that what this means, these definitions imply that the geometric realization of Y is exactly the Tietz building, which is a simplicial complex of dimension n-2. And the geometric realization of X is the barycentric subdivision of the n-2 skeleton of the complex of partial bases. Okay, so it's this complex where the vertices are partial bases and then simplices correspond to chains. Except because of this condition that I want only proper partial bases, I'm not taking the entire partial basis complex, I'm only taking the n-2 skeleton. I'm only taking the codimension 1 skeleton. Okay, sorry, so these, a reminder that these are in fact objects that we've just been discussing. Okay, great. So right, the next thing we need to check is that Y, which is our Tietz building, that this is Cohen-Macaulay, and this is a result that I'll attribute to Solomon and Tietz. And for those who are interested, so the statement that it's a wedge of spheres tells you immediately that it's the complex itself is n-3 connected, which is what we need. We also need this high connectivity result for the links. And if you read the lecture notes and exercises, then it will guide you through how you can understand these links as joins of smaller dimensional copies of the Tietz building. And so in fact, the Solomon-Tietz theorem again applies to guarantee that those are sufficiently highly connected. So that's outlined in the exercises if you're interested. For now, we'll just attribute the whole statement to Solomon and Tietz. Okay. And so let's look at the next condition. So the next condition is this condition on the fibers, on the downward fibers. Sorry, was that a question?
No.
No.
Okay, great. So for every subspace in Fn, this downward, in fact, let me go on to the next page because I'm running out of room here. Let's go on to page 9, and I'll just duplicate this page for myself. Okay, so here we are, we're on page 9. The next condition, is on these downward fibers. And so if you look back at the definition, then the downward fiber of a subspace V is going to be exactly the subposet of partial bases contained in V. And so its geometric realization is going to be exactly the barycentric subdivision of the partial basis complex on V, which is CM by this theorem of Mason. That was exactly the condition we need here. It's precisely this result of Mason that says these are Cohen-Macaulay when the ring R is Euclidean. Okay. And great. So that concludes our check of the conditions of the lemma. And so that means we can invoke Quillen's lemma. We can invoke the Quillen's lemma, and that tells us that we get a surjection from the top degree, or sorry, the n minus, it is the top degree, the n minus 2 degree reduced homology of X to the n minus 2 reduced homology of Y, which is our Tietz building. So this is precisely the Steinberg module of F. All right. And so if we can show that the image of this surjective map is generated by integral apartment classes, then we're done. Then we've proved generation of the Steinberg module for R Euclidean by integral apartment classes. And let me draw a picture. So remember this X here, this is the n minus 2 skeleton of our complex of partial bases for R. So let me draw a picture of, in the case n equals 2, let me quickly draw a picture here. So here's, if I choose a partial basis, here's B1, B2, and B3. And then you can fill in all of these points in the middle. For example, this one is the partial basis B1, B3, right there, and so on and so forth. And here, because we passed to the n minus 2 skeleton, we threw away the top dimensional simplices in our definition of X. There's no simplex in here. This is the missing simplex that corresponded originally to the basis B1, B2, B3 prior to subdividing. Okay. And under our map, the image of this triangle, this circle in the geometric realization of the poset X is going to be precisely the apartment class in, or the apartment rather, in the Tietz building that corresponds to this basis. So here's F B1. Here's F B2. Here's F. Oh, that was B3, sorry. Here's F B2, and so on and so forth. Okay, so the image is the apartment. Okay. So this is the idea of what we need to prove to finish our result. In this case, we can see the image of this particular subcomplex in X is precisely the apartment corresponding to this basis, and it's necessarily an integral apartment because X is built entirely out of bases for Rn, not for Fn, but for Rn, okay? And so if we can show that this homology here of the homology, this homology group here, the homology of X, if we can show that it's generated exactly by the boundaries of these missing top dimensional simplices, then that will prove that the image of this map is generated by integral apartment classes, and then surjectivity of the map finishes our proof. Cool. So that's what we want to do. So, right, so goal is to prove that this reduced homology is generated by the boundaries of the missing top dimensional simplices of B and R, since their images are exactly integral apartments in the Tietz building. All right. And the way that we're going to do that is by just looking at the long exact sequence of a pair associated to X in the complex of partial bases or its barycentric subdivision. Okay, great. So from the long exact sequence of a pair, what we get is an exact sequence. I don't want to tell there. Okay, so from our long exact sequence of a pair, we get this exact sequence, but this last term, this is 0 by Mason's result. So the Harevich theorem tells me that if those first n-2 homotopy groups vanish, then it's also true that these first n-2 homology groups vanish. In particular, this homology group has to be 0. And so what that means is that this connecting homomorphism has to surject but you remember from our algebraic topology classes that the connecting homomorphism in the long exact sequence of a pair is exactly comes from the boundary map. Okay, so we have this surjective map. Just rewrite this again. We have this surjective map. This is topologically, I mean, if we're just dealing with the underlying topological spaces now that we're taking homology, so we can forget about all this barycentric subdividing. Topologically, this is the codimension 1 skeleton of my complex of partial bases. And so going back to the definition of relative homology groups and working with simplicial homology, that implies that this homology group is going to be exactly the group of n-1 chains on the complex of partial bases, i.e., this is the free abelian group on bases for Rn. And the we remember that the connecting homomorphism, the map B, this connecting homomorphism takes an n-1 simplex to its boundary. Okay, so we got, this is exactly what we wanted. The upshot of all of this is that this homology group here is generated exactly by the spheres that look like this, the spheres that come from the boundaries of the missing top dimensional simplices in our complex of partial bases. So in other words, the image of this map is going to be exactly the integral apartment classes. Okay, so, right, so the upshot is that we have these surjective maps. Oh, sorry, I'm trying to go one step back.
I don't think you want reduced homology when you take relative homology.
Oh, thank you. You're right. That's a typo. Did I do that anywhere else? No, I don't think I did. Okay, great. So the upshot is that this map surjects, this compositive map surjects and the image is exactly the integral apartment classes. And so the upshot is that we have proved that, at least assuming this resulted Mason, we get Asteroidal. And in the last lecture in my series, which I'll give tomorrow, we will talk about how to prove Mason's theorem. So thank you. That's the end of my second lecture.
So I'll see if there are comments or questions. Don't seem to be, but that's probably a reflection that you're the 6th lecture we had today. So.
I'm sure, yeah, no, and I just talked for 2 hours in a row, so I'm sure everybody is destroyed.
But yeah, okay, so
everything from this lecture is explained in even more gory details in the typed up lecture notes. So if anybody's interested, take a look at that. And there are both more exercises and also some more structure given, more hints given toward the exercises that I mentioned in the lecture.
And tomorrow, before lunch, we'll have an exercise session with me, and we'll have exercises in the lecture notes, and she gave us some exercises, so we can go through some of those. You can work on them yourself or ask questions about them, and so that way we get some kind of knowledge attainment.
Okay, so thanks very much then again.